I'm very happy to be back after a couple of decades, or 15 years, a decade and a half. I'm going to talk about demonstration of potential connections of electro-weak coupling to unitary Weak-Boson kinematics, making a connection between kinematics and coupling constants. You've seen the abstract. My talk's gonna, first of all, I'm gonna give a little bit of background, how this work I've been doing was inspired by ANPA, and why it was needed in order to be usable by what Pierre Noyes was doing as far as combinatorial hierarchy. I'm gonna go a little bit into the fundamentals of quantum mechanics. I'm going to try to do that in a manner that's multidisciplinary. So I'll spend a little time on that, just so that you can understand my language. Likewise, I'm going to attempt to do that in a brief introduction of the standard electro-weak unification, Glashow-Weinberg-Salam theory. Then I will get to some of my own work on general formulations of fermi and boson fields. I will show how those fields don't have to be mixed in the configuration space in space-time, but can be mixed in momentum space. And once you do that, you're able to connect masses, which is a good thing. I will end with something that's, of course, would be dear to Pierre's heart, being able to plug in, say, the electromagnetic coupling and generate masses and other fundamental quantities in physics. And then I will have some acknowledgements. If it's up to me, you can ask questions all along, but I'm not sure about the time. I'll try to keep it moving, but I don't mind questions at all. So first of all, a little bit about my background. I'm a theoretical physicist. And so what do I think a theoretical physicist does? My idea of what a theoretical physicist is to establish the most elegant and simplest formulation that allows me to remember all the known experiments and to predict experiments that are consistent with that, with my memory of the known experiments. And in particular, I don't want to be seduced by mathematical elegance just for its own sake. That has mistakenly happened in the past. For instance, people were willing to give up energy momentum conservation just because neutrinos were being discovered, and they somehow broke energy momentum conservation, and you just wanted to have the fewest number of particles. You wanted the most elegant. Physics is ugly sometimes. It just, we have to model whatever is physical reality. So you don't want to get seduced by elegance for its own sake. This differs from the task of mathematical physics, primarily in that in training, I had to even know experiments, be familiar with experiments, do experiments, have intimacy and insights into the results of current and past experiments. So we're we're supposed to be anyway. Sometimes we aren't, but we're supposed to be close to the actual ongoing physical phenomenology. More of my background. My graduate advisor was a founding father during the formative years of ANPA, actually. While he was away at ANPA, I actually did some of the work at the first ANPA that resulted in some of what I'm going to be talking about. And I actually attended, I think, the second ANPA in 1981. I was on the ANPA Executive Council from 2004 to 2008, along with three of the founding fathers. Pierre Noyes recognized the need to be able to incorporate any of the discoveries that he might have having to do with combinatorial calculations. You had to be able to incorporate them into consistent high energy physics formulations that were, that could be connected to experiments. In other words, testability. He drilled this in me from the beginning. Certain basics about quantum mechanics and making sure that I understood the basic results of fundamental experiments. My PhD thesis and my first postdoc developed a relativistic few particle unitary and cluster decomposable scattering theory is published. I never presented any of that because it's sort of published in the mainstream. I never presented that at ANPA, other than to the extent that it was usable with discoveries made by ANPA efforts. In 2006, though, I did give 2 talks, one demonstrating the consistency of the formulation by actually calculating Compton scattering, which is scattering of light from charges. We did the lowest order expansion of the non-perturbative theory and got the result of QED, quantum electrodynamics, which is the mainstream way of describing the interactions of charges with light and photons. The other talk I gave was on an ANPA project that was originated by Ed, I can't read because my camera's in the way, by Ed Jones in the early 90s, relating cosmological fluctuations to a rising scale of decoherences, even prior to the discovery of dark energy. And in the meantime, many of the mainstream cosmologists have bought into that being true. So it's no longer appropriate, really, to talk about that particular ANPA initiated project in an ANPA meeting. I've been away for 15 years. I've written a couple of books on quantum gravity, but in the meantime, I still have always considered ANPA to be far and away my most favorite conference, and the individuals to be people of the highest regard. In that talk that I gave 15 years ago, we have a non-perturbative theory that allows you to, say, produce photons, lights the things that we use to see each other with, from a source and a detector. And the difficult thing about relativity is being able to disentangle. That's hard to do in relativistic quantum mechanics. It's just the opposite of classical physics. So we have disentangled source and detector. And this is what you want to have, a place to plug in couplings that are derived combinatorially or any other way. Let me explain what entanglement is. We know that matter is mostly empty space, of course, and yet we're not falling through our chairs and the floor. And that's because of quantum entanglement of the fermions, the electrons that we're made of. They don't like being in the same place at the same time. Even though they could slip between each other, they would have to be in the same state. So the reason we're not flowing into the meld is because we're made up of fermion particles that entangle. For this reason, I always felt more comfortable with quantum physics than classical physics. Classical physics has conceptual difficulties with action at a distance. Newton didn't like it. How do we touch, in other words? It was only until general relativity where you had local analyticity. Basically, this part of curved space bends this part, which bends this part. And that addresses action at a distance. Classical general relativity is not an action at a distance theory, and curvature can only be changed at the speed of light. So it also is a causal theory. But that really was the first classical theory that addressed being able to interact at a distance, really. On the other hand, relativistic quantum physics has difficulty describing how we don't touch all the time. How can it be that we can be fooled into thinking that we're classical beings, that we can disentangle and not have action at a distance? Part of the reason it's difficult is because of this terrible relationship of Einstein, E equals gamma mc squared. People may think it's E equals mc squared. That's just for particles at rest. If you're moving, you have this relativistic factor, and it's awful analytically, this square root. I have to be able to add energies together, and I have to be able to add momentum together. Try and do that in a square root. Oh my gosh. And have a theory. It has to be that it somehow happens when you go on shell. It's a non-trivial thing, and we succeeded in being able to do that with relativistic quantum scattering theory. So what was Pierre's, how was Pierre gonna implement, or how was he implementing this? Not gonna, he went a long way. What the combinatorial hierarchy generates are numbers that are inverse to the strong, the electromagnetic, and the gravitational couplings. You know, something that's strong, something that's weak, and something that's super duper weak, gravitational. Noyes had his combinatorial conjecture, which is that if I open up a quantum vertex, if I interact in some sense, the only way I can get out of that interaction is to open it up again in a mode that is consistent with the conserved quantum numbers. If there's 137 different ways that it could open, it's only going to open one in 137 different ways, and so that explains sort of the coupling constant of electromagnetism. We're mostly, most of the time, photons don't hit a charge. Only 1 in 137 times do they actually scatter. And so that's the way that you implement combinatorial type ideas into particle couplings consistent with relativistic quantum scattering. So I'm going to give you, as best as I can, my ideas of the fundamentals of quantum mechanics in a language. I'm going to try to make it so that those that are visually sort of geared toward visual, that I can sort of explain it. What quantum physics does is describe physical measurables in terms of calculable quantities that are encoded in these vectors. These things called quantum state vectors. They're vectors in a complex space. Observables like momentum or energy or mass or position, they're real, right? You never hear anyone measuring an imaginary, something that's imaginary length or something like that. They have to be real. And so that means in quantum mechanics, they have to be represented by special operators called Hermitian operators. And those operators always, they're Hermitian, that word just means that they have to give you real eigenvalues. And those operators generate infinitesimal changes in parameters that are conjugate to those operators. What does that mean? Momentum generates infinitesimal changes in space, right? So momentum and space are canonically conjugate to each other. And so space-time is clocks ticking and moving in space. Energy momentum is a different space, which generates changes in space in the case of momentum, and in time in the case of energy. Unfortunately, this allows any single measurement, any single experiment measuring momentum and position at the same time. It is physically inconsistent. You cannot do an experiment that's going to measure position and momentum. That's called quantum non-locality. And in addition to that, it generates a lower bound on how the different measurements differ from the average. The root mean squared deviation of different measurements of position from the average, that's uncertainty in position measurements and uncertainty in momentum measurements, cannot be made arbitrarily small. That's called the Heisenberg uncertainty principle. What happens when you have coherent interactions? You don't break coherence. So we're talking about states that are maintaining quantum coherence. They're in this quantum zone, whatever you want to call it. They modify the vectors without changing their norms. So the vectors keep their length, and somehow interactions modify their orientation in some sense and don't change their length. So that's called unitarity, or conservation of probabilities, because it turns out we always make the lengths equal to 1. And so that means the sum of all possible ways of looking at that length are going to add up to 1. So that's the basic formulation of quantum mechanics. If I detect a particle, though, that's it. That state is gone. It breaks coherence, and there's a new state. So a quantum state is only good if it's not detected. As soon as it's detected, it's eliminated. So detections are yes or no. No or yes, I would say, because of my advisor's name. Most of the time, no, and sometimes yes. You do not detect a probability any more than if we add up the average of all the rooms in your house, how many people are in there. You might say that there's 1.3 people in rooms, but you will never go in a room and see 1.3 people. That's just not the way it works. Even classically, that's true. But in quantum mechanics, it's inherently built in. You never measure the answer that you're predicting. You have to do many experiments to get that answer. The last point I want to make is that identical particles are utterly indistinguishable. They can spatially and temporally entangle. And so you're able to connect spins and statistics. I tried to come up with a way of expressing this. Suppose a position measurement, I have a screen that just reflects everything except blue. It will absorb blue, and it has an orientation that's related to position, and a different position will have a different orientation of the screen. Likewise, I have a screen that only detects red. It reflects blue. It has nothing to do with blue. It reflects it. And its orientation tells you a momentum. I have a quantum state vector, which is a unit length probability of one of it being itself, and it's purple. So it's got some bluishness to it and some reddishness to it. If I want to measure the position, I have to somehow shine some blue light on it. If I want to measure momentum, I have to somehow shine some red light on it. The projections, the shadows cast by that particular measurement, they only tell you the probability that I'm going to measure this momentum. That's all, the probability. Remember, you don't measure the probability, but the shadow cast, the wave function squared, at least that particular component, tells you the probability that that particular measurement will be made. The actual measurement is always a no or yes. So the projection only tells you the probability of a proliferously large number of no-yes measurements. Each measurement is a yes or no. This is what Pierre beat into me the first month that I was a student. The actual answers are yes and no, but the formulation predicts probabilities. A measurement breaks the coherence of the states, and the projections are never measured. You can think of it as a theory of shadows where the shadows themselves are never seen. So I'm going to show you a classical system where you're breaking coherence all the time and watching the system actually move. And so you would think it's classical, but it's actually a quantum system that you're watching all the time and breaking the coherence of the states, setting up new states. And I'm going to show you a quantum system. And these are real experiments, of course. This one you see all the time, and this one is the standard double slit experiment. Of course, with classical objects, you either hit the wall or you go through the slits. With this quantum, there's a chance of you detecting that you came by here. You don't know what the heck is going on here. You're doing quantum coherent propagation in between, and you get detected by either hitting this slit or hitting the wall. In fact, this experiment is one of the few experiments in quantum gravity that has been done. Neutrons from a nuclear reactor were sent through a double slit. And that experiment, well known back in the mid-70s, showed that whatever gravity is, It can't be little gravitons coming out and breaking coherence in order to determine MGH difference versus zero difference in the energies. The quantum coherence is maintained by gravity, whatever it is. Pierre actually nominated the guys who did that experiment for a Nobel Prize back in those days. So now, coherent interactions, as long as the system has not broken its quantum coherence, we are quantum beings, but we're breaking coherence all the time by forming relationships. But in those in-between periods, while coherence isn't broken, scattering theory is a theory that tells you as a system propagates in space and time, an initial quantum state vector that still is unit length varies to a final state state vector that's unit in length as a function of interactions that it might have undergone. The projection of that state vector in any particular direction, say this is position, that particular projection, the probability of it being at that same position has changed over time. And so that's what happens in scattering theory. For coherent states that satisfy the same energy equation, they satisfy the same equation of motion, those are called degenerate states. You can mix them. So I have two states that are sort of perpendicular, they're called orthogonal. And I can mix them into two other orthogonal states, defining a mixing angle. And so this mixing angle is going to wind up being like the Weinberg angle for those who are familiar with electro-weak interactions. So again, this is what happens while you're in the quantum zone of being a coherent quantum system until detections happen. And us thinking that we're classical is because detections are happening proliferously. Okay, next please, next slide. Okay, now I'm going to, as best as I can, give a quick overview of electro-weak unification. I want to consider the dynamics of a system as described using energies, we call them Hamiltonians, versus Lagrangians. Energy is the sum of energy of motion plus energy of position, so-called kinetic energy and potential energy. For instance, suppose I have a bowl with a marble. If I put the marble in the bowl, it'll start rolling back and forth, but since it's dissipative, it will eventually seek the lowest energy state, which is at the bottom of the bowl. So the energy doesn't tell us much about how it got there, but it does tell us what the most stable state is. And if the system can interact and dissipate energies, it will wind up in that lowest energy state. A better variable to use that we use a lot in theoretical physics is the Lagrangian, which is the energy of motion minus the energy of position, the kinetic energy minus the potential energy. This thing says that even if I throw a cannonball up, the energy is always conserved, but it follows a trajectory, that parabola. The Lagrangian is able to define a unique trajectory, even though energy is conserved. So you can't use energy to determine that trajectory. You have to use this particular technique we use to calculate unique energies. And so that's the reason we use Lagrangians a lot. We know quantum systems preserve probability. This is the probability that the state is the same as itself. That's always one. I told you the length is always one. Those lengths are invariant under any transformation that doesn't change its length. For instance, if I multiply by a complex number of unit length, the answer is going to be the same. A unit circle is called. So I can multiply by complex numbers that are unit length, and the length of quantum state vectors do not change. They remain invariant. That means the system is invariant because that change did not make a difference. If furthermore, I make that complex number depend on where I am, the so-called local transformation, it turns out in order for the system to maintain invariance, new particles have to be introduced. Those particles are massless. And a good example of one of those particles that have to be introduced is the way you're looking at my presentation called a photon. It is a gauge particle described by something called Maxwell's equations. And they carry the interactions between the quantum fields. So an interaction between me and you is being carried by photons so that you can sort of interact, your quantum states in the back of your eyeball interacting with light bouncing off of me. Now I'm going to talk a little bit about the standard Electro-Weak model, Glashow-Weinberg-Salam model. Weinberg is the person who taught me quantum field theory back when I was a grad student at Stanford. So it comes from, again, I told you Lagrangians. Lagrangians, we have to maintain that invariance of the length of the fields. Here's a field, the phi. I want the length to stay the same. So I have to introduce these particles. It's going to be a W gauge boson and a B gauge boson in order to preserve the length of that particle. And I have potential energy here that the field interacts with. And I'm going to somehow coherently mix the W with the B to produce a particle of light that we use to see each other with. So the photon is going to come from coherent mixing of the W boson with the B boson. And so that's what most of my talk's going to be about. And again, if you're not familiar with all the equations, I'm trying my best not to give the talk in that way, and you don't have to pay much attention to the equations, but some people are familiar with the equations, so I'm throwing them up there. The gauge bosons are massless. Well, that's not the weak particles, that's for sure. They're massive. They're short range, so something's wrong here. And they're perturbatively renormalizable. That's why these guys came up with this theory. If I have a potential energy that has a mass term, this thing, if the part that's quadratic in the field always generates a mass, this is a mass, and then an interaction term, the minimum is at 0. So the minimum energy is saying that nothing is there. And that's fine. That makes sense. That's a standard potential. The momentum, that's a standard mass. The lowest energy is not being there, and then it being there is a first excitation. That's particles. Excitations of a field. Little vibrations in the field are what particles are made up of. But if the mass becomes tachyonic, what that means is masses mainly travel through time. Tachyonic masses sort of travel through space rather than time, more so. Don't take it too literally, but in quantum mechanics, space and time are fuzzy, of course. It turns out the potential energy then has a negative term, which means that the place of minimum energy is not at 0. So that's a Mexican hat potential. The system will slide down into this new minimum energy state. And those who know calculus will just take the derivative and set it equal to 0. And this tells you where that new energy state is. And that generates a new field called the Higgs boson, or the God field. I don't like calling it that, the God particle. The Higgs boson, which lives in this broken symmetry world. Used to have symmetry. I used to be able to be anywhere. It's the same. If I were up here, I could look around any direction and everything looks the same. Once I go down here, I have picked a unique state to occupy, and that's called a spontaneously broken symmetry. This minimum is the ground state of the so-called God particle, the Higgs scalar. This is what happens in superconductivity. Superconductivity is I have electrons in in traveling through material that have very heavy nuclei. This electron goes by. The big heavy nuclei are very slow to respond. So by the time they respond, the first electron has gone by. The second electron looks at the first electron and sees more positive because of the response of the slow moving heavy nuclei than negative, and it's attractive. So that means I have two electrons actually attracting each other. They form a Cooper pair, and then they're boson. And they love being in the same place at the same time, rather than fermions like us not liking being in the same place at the same time. That's called superconductivity. So now we get to my, this is still standard electro-weak. So the standard electro-weak model generates masses for the charged W boson, the positive and negative charged boson. It then mixes the neutral boson with the B, this extra gauge field, hypercharge is called, but don't worry about the words, to generate a massless photon. And we know photons are very important. We are electromagnetic beings. So this is why we exist. Our atoms exist because of the electromagnetism. And neutral Z boson. These are heavy. So they are very short range. We don't see them much. They're responsible for neutron decay, beta decay. Massless excitations around the rim of that hat, the so-called goldstone modes, get absorbed and give longitudinal components to the W and the Z boson. Don't worry about all that if the words were too if you're not familiar with them. The only thing, the theory then says that in order for the W bosons to have the same charge as an electron, the gauge coupling has to be related to the mixing angle by this formula. Not only that, the mass of the W has to be related to the mass of the Z by the cosine of that mixing angle. And the place that the symmetry got broken satisfies this formula. Pay attention to this right here. That is a square root of alpha. So this is somehow kinematically, this is what would make Pierre happy, kinematically relating a coupling constant to masses and kinematic quantities. So as far as normal electro-weak theory, only the Higgs mass and the mixing angles are, the Higgs mass and the mixing angles are totally unconstrained. So what did I do? Or what have I been doing the past 30 years on this particular model that I've been working on? Actually, the model was inspired from the cluster decomposable scattering theory. So yeah, that's been more than 30 years also. So yeah, 35 years I've been working on this. I developed a single group theory for relativistic fermions and bosons. Fermions satisfy something called the Dirac equation. The Dirac equation has a form of matrices times momentum, giving you the mass of the particle. The problem with this, one of the problems with this equation is that, there's two solutions. You can have positive and negative masses. And so that meant that Dirac felt that the positive masses would cascade down into the negative solutions, and you would have the whole world falling into some negative energy state. So he hypothesized a Dirac sea that was already filled. And so if you knocked one of them out, that became an antimatter electron called a positron. My extension uses the same thing, except there's an additional eigenvalue associated with the gamma zero matrix, and the energy is therefore always positive. So you never have to worry about negative energies. There's no need to have any of that kind of interpretation. And it correctly describes, obviously, the Dirac algebra, which is the gamma equals 1/2 representation of the general algebra. Algebra is a group theory, the general group theory that that the fields satisfy. Dirac's representation describes all electrons, muons, everything, stuff like us, as well as all the quarks, any of the general fermionic structures like us. The gammas are 4x4 matrices that mix positive spin a half electrons, particles, with their antiparticles, positrons. They have to be held, they have to be mixed together in order for relativity to work. When they're at rest, they're separate. But the second they move at all, you're mixing particle with antiparticle. Just because it's tradition, from here on out, I'm going to put C equal to 1. I hope you don't mind. Just add it back in whenever you want. I'm going to call C equal 1 light unit. So the group theory of the first boson representation generates 10 by 10 matrices. Those matrices mix both scalars and vectors. That made me start looking at Electro-Weak immediately, of course, when I saw that. The quantum numbers include a scalar and 3 vectors, 3 particles with spin 1 and a scalar. If a particle is moving along the z-axis, this is what its spinor looks like, the spin state. It looks like this. It is written in terms of angles. That's really leading you toward thinking that angles, mixing angles are going to be able to be defined trigonometrically, except if it's massless. If it's massless, the polarizations are kinematically independent. You know that about photons. They just go the speed of light. The energy doesn't matter. So their polarizations do not depend on the kinematics. So defining this angle, when I found eigenstates of the 10 by 10 Dirac representation matrices for gamma equals 1, the eigenstates turned out to be able to be expressed in terms of these angles. Now I can have the ones that are neutral orthogonally mixed because gamma is 0. That makes them degenerate. They satisfy the same equation equal to 0. So I can mix a W spinor with a B spinor orthogonally to produce 2 new spinors, just like what's done in Weinberg-Salam. The orthogonal mixing requires that one of the spinors be mass-like and the other be tachyon-like. Tachyons, again, being necessary in the mixing somehow. And the resulting kinematic angles, I'm able to do algebra, and of course, this is why it's messy. I told you that square root is a mess, but you know, I've worked for decades, so you can believe me, the formula is right. There's going to be ugly square roots having to do with relativistic kinematic factors. But I'm able to find the angles that result from when I'm mixing a W and a B to produce a particle of mass M. So a W and a tachyonic B mixing to produce mass M. I write this as the angle associated with that. And the particle itself that gets mixed, you just add it all together, it turns out to be the same as this minus the mixing angle. Just cannot do better than this. So the mixing angle, but that actually generates the, whatever this is the mixing angle in, you know, that takes you from the WBs to whatever the mixed state is. So first of all, I want to be able to mix to a massless photon. Photons have kinematic angle pi over 4, as I told you, or minus pi over 4. That tells me whatever this thing is for a massless particle has to be pi over 4 minus the mixing angle. And you're able to analytically show that means that the tachyonic mass associated with the orthogonal B is the mass of the W times the tangent of the mixing angle. It analytically fixes the mixing angle for all energies B. You needed that to happen because remember, in electro-weak interactions, it occurred in the Lagrangian, which is space-time. I'm doing this in momentum space. If the mixing angle had depended on the mass, that would be a disaster. You want the mixing angle to be, you want to be able to mix in the space-time Lagrangian fields, and the momentum space just is allowing us to see what the masses are that mix. So it's beyond, it's supplementary to the standard model. Now I want to mix into a massive Z boson. There is a unique mixing, and it has to be that the Z mass is MW over the cosine. This is the Weinberg formula for mixing, but this is analytically derived for the unique solution where the mixing and the mixed are exactly equal and opposite with of the mixing angle. So that's fine. All that this has done up to this point is to derive in momentum space electro-weak mixing. However, in momentum space, I can now look at the masses and the kinematics. It turns out that a spinor in the representation of a mass of the Higgs that has momentum exactly equal to the momentum that it would need to have for a W with a Higgs to mix and make a Z is exactly the same as the mixing angle of the mixing that produces the Z. It is exactly the same. So now I get a condition that cannot be derived using standard electro-weak modeling. I'm able to so-called calculate the mass of the Higgs boson, for instance, which is good. Let's see how that turns out. So comparing the prediction to experiment, the only uncertainty, I'm gonna pick the Z boson as the standard, even though the Higgs is the more fundamental particle. The Z boson is measured from SLAC using electron-positron scatter annihilation to actually produce a clean Z boson standing still. So it's known to 5 significant digits. So 5, right? So whatever the predictions have to be, they have to be better than 5 significant digits. It's the best known, and so that's what I'm going to use for the calculations. I can either choose, from what I've done so far, to calculate the mass of the Higgs boson. It comes out to be the same as the one that's been discovered, within 5 orders of magnitude. The experimental uncertainty in it is only 3 orders of magnitude. So it's going to be a while before they could, can verify the actual numbers that you get with this part of the theory. In any case, it's about to be improved anyway. But in any case, it's better than way better, 2 orders of magnitude better, or 1.5 orders of magnitude better than what the experimental uncertainty is. Alternatively, I can calculate the Weinberg angle, the mixing angle. So the uncertainty based on the of my calculation is 6 orders of magnitude versus an experimental uncertainty of 4 orders of magnitude. So again, whichever one you want to calculate with that one additional relationship, it is falling well within experimental results. And in fact, it'll take still decades to be able to match the, to disprove the prediction. Both are well within experimental uncertainties, and so we're certainly off to a promising start. Now I want to go further, try to be a little greedy and see also the test to see if it really is a viable theory or model. I'm going to look at other kinematic correspondences. We saw that if I have the momentum of the Higgs spinor matching the momentum of the W and the Z, the spinor can be consumed in the symmetry breaking, leaving only a scalar Higgs. And so that sort of shows you how what used to be massless gauge bosons get a mass by gobbling up pieces of the Higgs, the right pieces of the Higgs that they need in order to have the correct momentum space representation. So if I'm now gonna look at energies instead of momentum. Whatever answers I'm gonna get have to just depend on mass ratios of the known particle. Yes.
James?
Yes.
Can you make sure you don't run over time?
Yes. Don't I have another 20 minutes at least?
Well, I think you've raised enough that there'll probably be a few questions.
Oh, okay. I haven't gotten, okay. All right. So you want me to speed up a little bit? Okay.
I don't want you to speed up. I want you to do it nicely, but make sure there is time for some questions.
Thank you. Thank you so much. I didn't realize I needed to do that. Thank you. So if you want to, what I did was just find another relationship having to do with energies. And so I went through and tried to figure out a minimum set of something that I could do to get an energy that would relate the Higgs with the W with the Z. And I was able to find that. I was able to find a relationship. And so it turned out to be that there was a correspondence at a mass of 245 GeV, which is like twice the mass of the Higgs. And I get yet another relationship. And this relationship is, with the present values, is 6 orders of magnitude, within 6 orders of magnitude of the measure results. So when I put together all the formulas, I get pure numbers, unique pure numbers for the Weinberg angle, for the ratio of the W to the Z, and for the ratio of the Higgs to the Z, pure numbers. If I look at the uncertainties, they're only due to the fact that there are experimental uncertainties in the mass of the Z. I predict a mass of the Z of 125.106, plus or minus the uncertainty of the Z boson, versus the actual measurement, which is 125.1 plus or minus 0.14, well within. It'll be a long time before, you know, they can exclude this. And likewise for the Weinberg angle. Now I have them both. I have them both. And the Weinberg angle is within 6 orders of magnitude of what is measured. The uncertainty is 4 orders of magnitude. So of course, this was exciting, and I wanted it to be first demonstrated since it's an ANPA inspired project at ANPA. Now, how does this relate to ANPA? Or how would ANPA people be interested in this? The electromagnetic coupling at the mass of the electron is one of the most accurately measured physical quantities. It's like 137 plus some decimal places. In the 1980s, David McGovern performed the combinatorially derived corrections to the 137 by utilizing Dyson's quantum field theory computation regarding the number of electron-positron pairs that can fit in a Compton wavelength before pair creation occurs. So he was able to get corrections that took into account the first few decimal points past an integer. Combinatorial hierarchy derives the integer, but you still have to be able to compensate for different physical measurements, which aren't just looking at the integer. Noyes and independently Bastian and Kilmester developed alternative combinatorial derivations using the Bohr-Sommerfeld equation to examine the fine structure of hydrogen. And of course, with perturbative quantum electrodynamics, 1 over alpha changes by 10% to around 127 near the mass of the Z boson. That occurs because you're able to start producing muon, anti-muons, quark, anti-quark, light quarks, and all that kind of stuff. So it sort of shields the electromagnetic charge a little bit. Kinematically dependent vertex factors. So there are two routes to complete unification. In other words, if you know alpha, you're able to get all the masses. One of the routes is directly using the spinor here, whose symmetry is broken. That spinor introduces a mass scale. And so that mass scale is kinematic, and it's related to the square root of alpha. In international units, it's the square root of 4 pi alpha. In Gaussian units, it's square root of alpha. And so you can come up with some, combinatorially or any kind of derived relationships that relate kinematic values with coupling. Alternatively, I can look at the normalization of the photon field that occurred from the mixing and see if that normalization allows you to directly complete the unification and have the coupling constant determining everything if this is a physically correct model. So the kinematic mixing involves all, it's non-trivial. I just put the graphs of all the stuff. This is a W-Boson mixing with a B to produce something else. This is a Z mixing with itself to produce, for instance, here's the Z. Here's the vacuum expectation value of the thing that becomes the Higgs field. All these things are on kinematic. Sorry, wrong way. All these are kinematically determined. The second way was with normalization. I've gotten some answers that are close, but the factors kind of sometimes upside down. You literally are able to calculate the mass of the Z from the alpha. If this is the right answer, if this is the factor needed for normalization, to 5 orders of magnitude, which is better than what is known. This is barely, again, involving this expectation value of the vacuum field with other factors that are easy to kind of understand, but still it's a little bit upside down to me. I haven't yet been able to derive these kinds of numbers. But if such a relationship can be found, it basically says that the couplings are totally determine the actual kinematics of electro-weak interaction, which is complete unification. I'd like to have some acknowledgements, of course. First of all, I know Pierre would take this and run. A formula that's actually able to do the kinematics that he wanted with input of coupling. Pierre was a man of complete integrity and brilliance, and he had genuine and honest openness. Those of you who knew him knew know he was a true prize and character. And also the founding fathers of ANPA. ANPA again is one of my most favorite and supportive groups that I actually love coming to ANPA conferences. These are characters of impeccable repute and respectability. Thank you folks so much for your time. If you have questions, let me stop sharing. Thank you.
Okay, fantastic stuff. I suggest people unmute themselves and come on the video, and then maybe somebody would like to ask the first question.
Could I ask about the mass of Higgs?
Absolutely.
When did you actually calculate this? Did you manage to get a calculation before they found it experimentally?
No. I did the first calculation about a year ago. I knew to try to that I could mix. I actually wrote papers saying I could mix the neutral with the vector. And let me be completely honest. It would have been very difficult to discover the subtle relationships that sort of show you how the Higgs, the components of the Higgs get consumed in order to produce the massive bosons, which of course the standard model doesn't tell you anything about. So I'm going to be very honest. I needed the Higgs to be discovered to do the original sort of correlation, not all of it, but the correlation of actually seeing how that's done. I needed the experimental.
Could I ask another question?
Mm-hmm.
The physicists, my colleagues, talk a lot about the coupling between the Higgs and fermions and coupling between the Higgs and bosons, and saying that that's totally dependent on the mass and so on. You have an independent way of getting this coupling.
No, that's part of one of the big mysteries and problems of high energy physics is it's a Yukawa coupling you're talking about.
Yeah.
Every particle has a completely independent Yukawa coupling. So as many it doesn't do anything. In other words,
well, that determines the mass.
Every single mass.
Yeah.
Now, of course, the coupling to the W and the Z, of course, I did show, but it's not really telling you anything new if you have as many couplings as you have particle masses, and not only that. For instance, the masses of the neutrons and of the hadrons of the nuclei is mostly due to the kinetic energy and potential energy. It's not even due to the Higgs. So most of our mass is not due to the Higgs.
Well, I don't agree with that. I
Yukawa
think it is due to the Higgs.
The
Even though it's kinematic, it's still due to Higgs. I could explain that.
No, it's due to the energy.
No,
The
but I don't
kinetic-
think they're mutually exclusive.
Oh no, of course not. But I'm just saying most of the energy is kinetic and potential energy by far. I mean, even if the mass of the even if you said the Higgs completely gave mass to the quarks, which would mean that self energies didn't count. But let's say the mass was completely due to the Yukawa coupling, you still would have hadrons weighing much more than the sum of the masses of the quarks. That's all I'm saying.
Okay.
Why don't we see if there's anybody else who wants to ask a question? Lou?
What is your view at the present time of the old calculations of the fine structure constant using ANPA ideas?
They have not changed. I've always been supportive of those. Those are things I haven't worked on. In Pierre's case, I was his sounding board, and I was also gave him criticism and helped out with making sure there was no conceptual flaws and little minor calculations. But I was never involved in the creative part of that. Mm-hmm. Pierre didn't really want me involved in the creative part of the ANPA when I was first a grad student, because I think he wanted me to be able to focus more on the other supportive apparatus that was needed. So I have never really been involved other than as a sounding board, criticizer, and a polisher with the actual combinatorial hierarchy calculations, including yours, because didn't you? I think you were involved with
not directly with combinatorial hierarchy, but yeah.
I mean, with the elliptical, weren't you involved with modifications to the fine structure constant? Didn't you do a calculation?
No, I never did any calculations about that.
Okay.
But I think that at some point it would be very good to have a review of what happened there and what might be done with that. And we really need somebody who's a good physicist to work together with whatever is known about that. So maybe we could create a project to look at it again at some point.
I'd be honored, of course, to work with you. We've never actually worked together, but of course we ran into each other at Slit, so it's at ANPA.
Anybody else for a question?
That's his that's low.
Okay. Peter Rowlands looks like